Swayam Prabha. Digital India. Educated India.
Hello all. So welcome to Astrochemistry. This is lecture 13 and this is tutorial 3. In the last tutorial, we ended up with a discussion on ideal gas law, the ideal gas law, and discussing its validity. And we stopped by discussing that the equation PV equals nRT is more valid, at conditions of very high temperature, wherein due to the increased kinetic energy of the molecules, the interactions can be ignored. The molecular interactions can be ignored readily, and also at very low pressure. And due to very low pressure, the molecular size and the interaction can also be ignored. Okay, so this is why the ideal gas law, that is PV equals nRT, is significantly more valid at regions of high temperature and low pressure. All right, but we'll continue with that discussion. Sorry for that, but that was an irrelevant word. So we shall be continuing with our discussion on the validity of ideal gas law for different regions of the ISM in this tutorial. So if you recall, in our earlier lecture, I think this is going to be the first question for this tutorial. It is that we discussed that PV equals nRT, okay, this equation was not valid in the ISM even at approximately 10 to the power 6 Kelvin. Why is it meaningful? What do I mean? Why is it true? After all, we just ended last tutorial. We just ended the last tutorial. This is page 1. We just ended last tutorial by saying that the equation PV equals nRT after all holds good at high temperatures and low pressure. And in fact, at such very high temperature, the pressure is almost zero, right? It's as we discussed in an earlier lecture. So after all, the temperature is very high and the pressure is very low. But why is the equation still not valid? What is the answer to this question? The answer to this question is that this equation, in this equation, PV equals nRT, the P is the thermal pressure. And what is the thermal pressure due to? It is the pressure exerted by the molecules of a gas. Okay, but at such very high temperature where almost nothing can exist, the number density, recall again from an earlier lecture, if I'm correct, it is lecture 8, okay, or lecture 7 maybe. Yeah, it is lecture 7, more likely to be. You may double check. So in lecture 7, we discussed the number densities at various regions. And at 10 to the power 6 Kelvin, again, if I'm correct, the number density was less than 1, definitely less than 1, and probably of the order of 10 to the power minus 1 or minus 2 in fact. Okay, it is so low. It was so low, right? So when the number density is so low, we don't even have so many molecules present. Okay, so when the molecules are not present, the sanctity of this equation, the pressure itself, the net pressure in that milieu or that environment is completely due to okay, so the net pressure, the pressure at such a high temperature of like approximately 10 to the power 6 Kelvin or so, P is only due to majorly due to magnetic and gravitational turbulence. Okay, so when the pressure exerted is completely due to this, and we're not talking about P in the limit of 0, okay, right? Which was the case at approximately 10 Kelvin. Over here, there are not even enough molecules for this equation to be valid, okay? So that, when there are enough molecules, then we can form a Gaussian distribution of the velocities, okay, which is called as the Maxwell-Boltzmann distribution, and based on that, we can assume thermal equilibrium conditions, and this equation can be valid. So, through this question, I want to emphasize the idea to you all that just because the temperature is high and the pressure is extremely low, but one cannot say that this equation is valid under all conditions. The validity of the equation, okay, the PV equals nRT. So PV equals nRT is valid, okay, A, at low pressures, B, high temperatures, and C, the number density, okay, should be sufficiently high. The number density should be sufficient for some sort of a local thermal equilibrium to hold good. For to be holding good. Okay, so please note it. All right, so to these two questions, that is, the use of ideal gas equation at very low temperature and at very high temperature in the ISM, look at how many fundamental ideas we are actually revisiting and appreciating. So in high school, we may only be considering these two facets, but this idea is also equally important. All right, and that the pressure and under such a very highly unimaginable environment than what is encountered on Earth is not due to the molecules, because most of the pressure that we encounter on Earth, right, it is due to some molecules, right? But the pressure in the interstellar medium need not always be due to molecules, especially at some extreme temperatures. The pressure can be majorly due to magnetic and gravitational turbulence, and so this equation can be redundant at such high temperatures also. Are we clear? So on that note, having discussed enough about the ideal gas law, we shall proceed to our next question. This is an interesting question. Let's see how you answer it. So the question is as follows. This question kind of, I'll give you a hint, okay? Even before giving you the question itself, this question is kind of based on a logical fallacy. What it is and how we discuss it, we shall see. So the second question for the day is, we know, okay, it's a fact, liquid water exists on Earth. I'm sorry. I mean, it's an obvious fact, right? We must have all, we are alive because we drink water, correct? Yeah. So liquid water exists on Earth. It's also a fact. I'll call this fact 1. Let this be fact 2. Is that liquid water does not exist in the ISM. We looked into this through our lectures, right? I, in fact, was drawing the phase diagram probably in lecture 8, and I was discussing about the various facets of the phase diagram and how we know the triple point of water, which happens to be at like very low pressure, significantly less than 1 atmosphere, and around 273 point some Kelvin, right? So at that temperature and pressure, that combination was not possible in the ISM. So liquid water does not exist in the ISM. So this is a fact. It's true. It's not false. This is also a fact. Okay. And given this fact too, ISM, what is the interstellar medium? It is the space between stars. Okay, right? So given these three facts, the question is, therefore, we on Earth, so given all these facts, Earth is also between any two stars. But water is present on Earth, but liquid in the liquid state, but it does not, but liquid water does not exist in the ISM. So how to reconcile? How to account for no water, no liquid water in the ISM? Are we clear? Recall the hint I gave you at the beginning. There is some logical fallacy somewhere, right? There is liquid water on Earth, and in the ISM, we discussed scientifically that liquid water does not exist in the ISM. And the ISM is nothing but the space between two stars, which is also what we've been discussing, right? Starting from probably lectures 5 or 6, perhaps. Okay. So, given all these statements, how to account for the fact that there is no liquid water in the ISM? What is the answer? Recall the hint I gave you. The hint I gave you was that this is a question based on a logical fallacy. So what is the answer? I'll quickly delete this part. It should give you enough time to think about it. The answer is that, look here carefully. The hint is here. Okay. The answer is actually the idea that answer fact 3 is incomplete. What are we missing here? We are missing the idea that the ISM is not just the space between any two stars, it is the space excluding the disk space, right? Recall. And obviously, the Earth exists on this disk. What is this disk? This disk, surrounding any star is going to be the region wherein all the celestial bodies and molecules, right? They're all going to be under the gravitational influence of the star. So Earth, of course, is under the gravitational influence predominantly of the sun, mostly of the sun, and maybe some other star, but to a much lesser extent. Okay, right? So because the Earth falls within the disk space of the sun, for example, right? We do not consider Earth to be part of the ISM itself. All right. So the key thing to note is this is not a complete fact. This is incomplete. Okay, this is incomplete. This statement right here is incomplete, and that is why this question is based on a fallacy. So it is a fallacy that Earth is part of the ISM. So why did I ask this question? To drive home 2 points. One is the detail. Okay, so it looks very easy to understand that the interstellar medium is nothing but the space between two stars. However, there is an added layer of detail. It is that one has to exclude the disk space. Okay, and through this, we come to understand that even though the Earth is, of course, between any two stars at any given point in time, we do not consider the Earth itself to be part of the ISM. All right. So this is the message from this question overall. We'll move on to the next question. I'll delete all of this now. Okay. So what is our next question going to be? Our next question, okay, is also interesting. It's not exactly based on a fallacy, but it's somewhat over there. All right. So it's again about the liquid water. Okay. So the question is, we saw in the lecture, okay, I'm sure it was lecture 8. Okay, from lecture 8, we saw that liquid water does not exist in the ISM because no H2O liquid in the, because the phase diagram looks something like this. That's the ultimate answer, right? Because you consider P versus T, and the phase diagram looked something like this, and this is the triple point. I'm just going to call this TP, and the coordinates at TP will be some P less than 1, significantly less than 1 atm, and T approximately 273.16. So no matter what the temperature is, right, because in the interstellar medium, the pressure is even less than this, right? We do not have the formation of any liquid water at all. This was our understanding. But the question now is, let's say that, okay, but what does it tell you? It also tells you that, it not just tells you that liquid water alone does not exist in the ISM. In ISM, a fact based on this data is that in the ISM, this specific equilibrium is not possible, right? Not just this equilibrium, we don't have the liquid to gas because the liquid doesn't exist. We also don't have, it's not just this equilibrium, H2O liquid, H2O gas. This is not possible. You can have, under some conditions, you can have the solid and gaseous state to be in equilibrium, but never the liquid, okay? But when you open, let's say that you have some ice cubes kept in a fridge on Earth, okay? This is an ISM. Now on Earth, okay, let us say that you open your ice cubes, okay? You open your ice cube, right? You've kept some water in an ice tray, and then you keep it inside the freezer where the temperature is very low at 1 atmosphere. And then once you open it, you have the ice cubes in your hand. Now, what will happen? The ice cubes will not just melt, they will also sublime, correct? On Earth, once you take out ice cubes, take ice cubes from the freezer, approximately, you take it out to T equals 300 Kelvin, and the pressure being 1 atm. You notice that it is not just, like H2O solid to liquid, it's also H2O solid to gas. You don't see this equilibrium though. Am I clear? You see two equilibria at this point, right? You see that the ice sublimes to some amount of gas. You see that, right? Along with that, you also notice some solid to liquid. Are we good? I will remove this fact in the ISM because this is not happening on Earth. Are we clear about my statement? Okay, so this is happening now. But according to the vapor pressure, right? Look at the coordinates of TP. This point, okay, right, is less than 1 atm. And what is this? This is the gas phase. This is the liquid phase, and this is the solid phase. That's what we looked up from the phase diagram. Okay, so this specific point, okay, this specific point TP, the pressure is less than 1 atmosphere. But on Earth, we see the pressure to be 1 atmosphere. The pressure is 1 atmosphere, and so your solid and gas equilibrium, okay, the solid phase and gas equilibrium is only possible at temperature, at pressures which is significantly less than 1 atmosphere from this phase diagram. Yet, we see this happening on Earth when you open your freezer. So the question overall, okay, after so much rambling, about the various statements, because I had to put the question in the context, okay, the question is the phase diagram even, I'm just calling this the PT diagram, okay, is the phase diagram even valid on Earth? Given this thing, right? Given either, I must be making a horrible mistake in the phase diagram, which I can confidently tell you I'm not doing, point number 1, okay. That not being the case, how is it valid? Because this point is at significantly less than 1 atmosphere, so 1 atmosphere shall be above it, right? And at any point above on this graph, there is no solid gas equilibrium at all. But when you open your freezer, you do see this happening on Earth, right? So how to reconcile this apparent paradox? Either we know the phase diagram is not valid at room temperature on Earth, okay, which would nullify all our hypothesis, or what point are we missing? What are we missing here? What logic are we missing here? What's the answer? Can someone guess? I'll give you a hint, okay? The hint is, look into what this P is. What this P is doing here. What variable does it correspond to? The pressure here, right? The pressure in the phase diagram, okay? The answer is again that P in the PT diagram corresponds to pure pressure, right? It corresponds to pure pressure of the substance. This is a massive hint. This is an absolutely massive hint. What do you think is the answer? Given this hint? Well, it is that on Earth, when we see that, we also see the solid gas equilibrium. That is, we also see some small amount of ice cube, not just melting, but also subliming, right? I mean, this is going to be negligible. This equilibrium will also be there, but it's negligible, okay? So some solid also subliming. What is it happening under? It's of course happening under atmospheric pressure, but it is happening not under vacuum. We not only consider the pure pressure there, okay? So we have to consider the partial pressure of the ice, okay, right? Amidst air. Air exerts its own pressure, right? So therefore, in our houses, for example, when we take the freezer, in the freezer example, P is not pure pressure. And that is why we do not get results in accordance with this diagram. All right. So the presence of other gases, okay, right, ensures that the pressure exerted by water vapor is only a partial pressure amidst all other gases. Whereas this diagram is valid when we consider only the pure pressure of the substance. Are we clear? It looks to be a subtlety, right? It looks to be a subtlety. And what does it teach us again? What is the moral from this question? The concepts that it teaches are, I will delete the whole phase diagram now that we don't need it. So the message from this question is, be careful when comparing theoretical ideas such as, for example, the phase diagram versus conditions wherein the parameters are changed. So what I've written here is conditions wherein the parameters are changed. Okay. So be careful when doing it, because in the phase diagram, what we encounter is the pure pressure, whereas in reality, what we compare is actually the partial pressure, and that is why we also have the solid gas equilibrium possible, which per the phase diagram is actually not possible. Okay. So through this question, we again are able to understand the beautiful connect, between fundamental science, fundamental thermodynamics, the fundamental understanding of phase diagram with what we understood through the chemistry happening in space. Overall, beware when comparing different things. You should be having a very clear idea that any formula or any graph that you're using is exactly applicable to the problem at hand. Okay, so this is just a scientific message I wanted to convey through this problem. We shall now move on to our next question. Okay, Now this question it's kind of a fact-based question, but still very important. I think this is going to be question 3, right? If I recall. No, maybe question 4. The first one was the ideal gas one. The second one was the was it 3 or 4? Maybe 3 or 4. The exact question number doesn't matter. I lost track of the question number though. Okay, right? Yeah. So the question is, what is the astronomical unit system? Now this is a fact-based question. I mean, because it's an astrochemistry course, you shall be encountering, if you read further, right, outside this course, if you read various textbooks and journals, you will be finding various astronomical units mentioned. Okay, so I just thought that it would be a nice idea to take you through the astronomical unit system. It's fact-based. Okay, so you can relax after a series of heavy logical thinking. Okay, so this is going to be fact-based for the most part. So the astronomical unit system gives us, different units. Okay, it was found that, see, when we consider the dimensions in space, okay, you consider the distance between any two stars, or forget that, even the distance between any two planets, or between a planet and the sun, etc., etc. The distances are huge. So the SI units are not found to be exceptionally useful, correct? What are the SI units? The SI unit for length is what? The SI unit for length is meters, correct? For mass it is going to be kilogram, okay? But what is the distance between the Earth and the Sun? It's a huge number, right? Even without doing any calculation, you can understand that it's a huge number. Likewise, what is the mass of Earth? How many kilograms is the mass of Earth? Of course, it's a variable number, considering that the population may change, and also that the atmosphere around us is, it keeps undergoing so many changes. What is the overall mass of the Earth? It's again a very huge number. Let's not worry about the exact number yet. I'll answer it as part of this question. Okay, it's a huge number. So therefore, it was decided that the astronomical unit system be used to study fields such as astrochemistry, astronomy, astrophysics, etc., in lieu of using the SI units, which would present the use of highly inconvenient numbers. Okay, so we have different astronomical units for length, and we also have it for mass, and we also have it for time. Okay, in this lecture, I will just stop with giving you the astronomical unit for time. Okay, it is because it's the simplest. In the next tutorial and the next lecture, I will continue by discussing about the astronomical unit for mass and length. Okay, so for time itself, it's very simple. It's the day, which is exactly defined to be containing 86,400 seconds. It's simple, right? How do you get this number? 60 times 24. Okay, right? A minute has 60 seconds. Okay, and each day has 24 hours. Okay, right? That's it. That's about it. So 60 for the seconds to minute, and the minute to hour, and the hour to 24. That's it. 60 times 24 will give you this number. So on that note, in this tutorial, we saw a couple of logical fallacies about the validity of the equation of state, and also about liquid water, present in the ISM, and how we should be careful about using various graphs and comparing them with conditions wherein they may not be applicable. And lastly, I stopped by introducing you to the idea of the astronomical unit system. I will continue with this question in the next tutorial. I'll also clarify whether it's 3 or 4 in the next tutorial. Okay, thank you so much. Have a good day.